Hello everybody, welcome to Math 127 at Christopher Newport. Today we are going to start talking about permutations. Just a word of warning, I sort of put this together very quickly. I kind of forgot that I had to do it, and the delivery may not be the smoothest as such. All right, but let's get started. All right, so far we have seen a variety of different types of ciphers. We started the semester looking at monoalphabetic ciphers. We saw that they were actually very insecure. They would eventually fall to frequency analysis, if not something easier than that. We moved on to polyalphabetic ciphers. In particular, we looked at a partition cipher and we looked at Vigenère cipher. We saw that those also had their weaknesses. One of the biggest problems with polyalphabetic ciphers is that people didn't use them properly, and so they got cracked very easily as a result. From there, we went on to polygraphic ciphers, ciphers that encrypt blocks at a time. We saw the Hill cipher as a first example of a digraphic cipher using matrices, and while that was only a 2-block, you can make Hill ciphers that are larger. And then we saw the exponential cipher, which we then used to create public keys, crypto systems, and Diffie-Hellman key exchange. So these have gotten steadily stronger as we went, but they're not enough, okay? While these have gotten stronger and stronger, they still have some shortcomings. One is that RSA is very labor intensive, and frankly, it's not great for a lot of communication. Realistically, the way that RSA and other public key systems are used is you use those to do the initial setup on a private key system. So you would contact your other party using a public key system. You would exchange a few messages to establish a private key system using the RSA system, and then move over to private key. The other thing is that while exponentiation, the exponential cipher, is very secure because of the discrete log problem, it's also computationally intensive. The other thing is that as we increase the size of, or the computational power of computers, we have to keep moving the modulus up. We'd like something that would remain static for a while. Now, there is no guarantee or expectation that you could find some crypto system that was fast, reasonably secure, that would last forever. Computers will eventually become powerful enough to crack most systems. So you will have to advance it from time to time, but we don't want to have to be doing it constantly. So we come to a very interesting man by the name of Claude Shannon. Claude Shannon was a mathematician and computer scientist who made great strides in the areas of cryptography and what's also called coding theory, or error-correcting codes. He developed two ideas, two concepts for cryptography, and he labeled them as confusion and diffusion. Okay, confusion is where you're going to have encryption operations where you obscure the relationship between the key and the ciphertext. So case in point, if you look at the exponential cipher, because of discrete log, you have very little relationship that you can easily see between ciphertext and the key. You can't solve for it. Vigenères do a good job of confusing the key if the keyword is reasonably long, or if you're using something like a book cipher. Monoalphabetics, yeah, there's nothing there. It's very easy to recover the key. A known plain text attack will do it in a matter of seconds, really. So the other operation he talks about is diffusion. All right, so this is an encryption operation so that the influence of a single plain text character is spread over as many ciphertext symbols as you can. All right, this is good at trying to essentially hide statistical properties like frequency analysis and other things like that. So a couple of examples, we've seen digraphic and polygraphic. They are good at adding diffusion. Okay, So they will defeat things like frequency analysis, but they're still not perfect, because if you're looking at something like a digraphic cipher, okay, so you can't do frequency analysis on single letters, but you can start to do frequency analysis on doubles of letters that appear commonly in languages. So they're not perfect there. All right, so we want ways to add diffusion as well as confusion to our existing system. The way to do this is to use a new type of mathematics. All right, pretty much all semester long, we've been looking at ciphers that are based on modular arithmetic. And modular arithmetic is critical to cryptography. But the fact of the matter is that it doesn't do a very good job of obscuring the fact that we are encrypting known words. All right, so what we want to do is break up the words themselves. We want to break up the English so that we are no longer encrypting straightforward English text. To do this, we're going to use a mathematical concept of permutations. Now, you've probably seen the word permutation before and may have an idea of what it is. Mathematically speaking, we have very strict rules for what a permutation is, and we'll look at those now. Okay, there are two ways to consider permutations. They're very closely related, but we'll look at both. You'll see that one is mathematically better than the other. But the first one we'll look at is a permutation of the numbers 1 through n is a listing of the numbers such that every number between 1 and n appears in the listing and no number is repeated. Okay, this probably jives with your understanding of the word permute or permutation. We're just going to reorder the numbers. Now, when we reorder them, we have to make certain that every number gets in the reordering and we never repeat a number. All right, so let's look at a few examples of permutations of 1, 2, 3, 4, 5. All right, so one way to reorder them is to, well, not reorder them. You just leave them in the order you have. All right, this is another reordering. Okay, there are all 5 numbers appear, 1, 2, 3, 4, 5. There are 5 numbers in the list, so nothing can get repeated. Here's another one just for fun. All right, this one is not a permutation of the numbers 1 through 5 because it's missing 5. This one's not a permutation because it's missing 4 and it repeats 2. All right, and this one is also not a permutation because it's omitted 4 and it's repeated 1. Okay, so in this sense, as I said, it's just a matter of reordering the numbers you're working with. Now, there is a more mathematical way of representing a permutation. So what we say mathematically is that a permutation of the numbers 1 through n is a function that maps the numbers 1 through n to 1 through n, where if I is different from j, then the function, we usually denote them by Greek letters. In this case, we'll use sigma. If I is different from j, then sigma of I is different from sigma of j. And for all j, there is some I such that sigma of I is equal to j. Okay, what does that mean? Okay, let's look at an example. The easiest way to do this, to represent such a matrix such a permutation, is to use a matrix. All right, so we're permuting the numbers 1 through 5. So we put those here, 1, 2, 3, 4, 5. Those are the inputs of my function. All right, and then the second row contains what everything gets mapped to. So sigma of 1 is 2, sigma of 2 is 3, sigma of 3 is 1, sigma of 4 is 5, and sigma of 5 is 4. Note, sigma of I, when I and j are not equal, then sigma of I is not equal to sigma of j. That means that in this second row, I can't have a repetition. Okay? For all j, there is some I such that sigma I is equal to j. That means if I'm permuting the numbers 1 through n, the numbers 1 through n have to appear in this second row somehow. All right, so the connection then between our first sense and our second sense, this second row, that's just a relisting of the numbers 1 through n, where again, no number is repeated and every number appears in the list. So the two ideas are basically the same. Okay, so let's look at how many permutations there are for a set of numbers 1 through n. Okay, so let's start small. Let's start with a list that contains only one number, namely, well, 1. Okay, well, I need all listings of one number where the number appears exactly once. Well, there's only one way to do that. Just write the number itself. Okay, so now if I want to look at permutations of two numbers, so I need the numbers 1 and 2. They have to appear, both numbers have to appear in the listing, and nothing gets repeated. All right, well, there's really not many choices there either. I can start with 1 and then have 2, or I can start with 2 and then I have to have 1. All right, if I'm looking at permutations of 1, 2, and 3, well, now I start to get more options. All right, so I could write all the orderings that start with 1. So again, one way to order it is not to reorder it at all. I could just have 1, 2, 3. Then I could start it with 1, and if I don't want the next number to be 2, well, there's not much choice. It then has to be 3, and then I need to have 2 so that I have all 3 numbers. Okay, but what if I don't want it to start with 1? I could have it start with 2. All right, well, if I have it start with 2, then the next number either has to be a 1 or a 3, and then the third number has to be the other one. So if I have 2 and 1, then I must have 3. If I have 2 and 3, then I have to have 1. And then, likewise, I could start it with 3. Then, same deal. Once I start it with 3, this second number either has to be a 1 or a 2, and then the third number has to be the opposite. But then that's it. This is all the ways to start it with 1, all the ways to start it with 2, all the ways to start it with 3. So, when n is 1, we get 1. N is 2, we get 2. N equals 3, we get 6. Okay, so let's look at 4. Now 4 is going to be much larger, as we will see. But any permutation, well, let's break it down. We're going to break it down by those that start with 1, those that start with 2, those that start with 3, and then those that start with 4. Okay, so if we start with 1, okay, well, there are, it looks like, 6 of them. All right, because once I start with 1, then I have to put the numbers 2, 3, and 4 in some ordering. Well, they may be the numbers 2, 3, and 4, but they're 3 objects. We know how to order 3 objects. We saw that on the previous slide. Whoops. There are 6 ways to reorder 3 objects. So, when I start with 1, I have 6 ways of reorganizing 2, 3, and 4, and that gets me 6 permutations that start with 1. If I start with 2, well, it's the same thing. I've got 3 numbers left over. All right, so they're the numbers 1, 3, and 4, but they have to appear in some ordering. There are 6 ways to do that. So I get 6 options there. Likewise, I will get 6 options with 3, 6 options with 4. All right, so that gets me a total of 24. Now, the question becomes, do you notice a pattern? So the total number of permutations, we started with 1, then we got 2, then we got 6, then we got 24. All right, so that leads us to what's called n factorial. Okay, so the number of permutations of 1 through n is simply the product of the numbers, well, 1 through n. All right, this is called n factorial. Now, the reason that this happens is sort of easily seen in that previous slide. I had 6 ways to reorder 3 objects. So I had 4 things that I could start it with. I had 6 options for each one, which is 4 times 6, which is 24. Where did the 6 come from? Well, I had 3 ways to choose how this starts, and then I had 2 ways to order the other numbers. So there was 3 times 2 times 1. So the number of permutations is going to increase by n every time we increase n. All right, now n factorial gets very big very fast. To give you an idea, all right, let's just look at the first 10 factorial numbers. All right, so we get 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 24, 5 factorial is 120. All right, by the time we double from 5 to 10 factorial, we go from 120 to 3.6 million. Okay, so doubling the numbers has increased the size of this thing by 4 or 5 orders of magnitude. And every increase in by 1 from here on out is going to give you at least another order of magnitude. All right. Factorials get very big very fast. If you remember from the first week, I showed you in Mathematica that, calculators can handle factorials up to about 68, 69. Yeah. And this is part of the reason we use Mathematica. It can handle a lot larger values for the factorial. All right. But to give you an idea of just how big factorials get, this is 1,000 factorial, and it's literally lines upon lines of numbers. Okay, so let's go back to thinking about permutations less as reorderings, but more as functions. Now, one of the reasons we want it as functions is that permutations as functions can be composed. If you remember from, algebra 2, etc., you looked at f of g of x. We are going to do that with permutations. So when we compose functions, we take our input value, we apply the first function, and then whatever comes out of that, we apply the second one to it. Okay, so let's look at, say, tau compose sigma, this is a Greek letter tau, by the way, as a total permutation. All right, so what we're going to do, we're going to take our input value, we will plug it into sigma, see what we get out, take that number and plug it into tau and see what happens. So, for example, if I plug in I equals 1, well then sigma will get me 3. I then plug in 3 to tau and I get 5. So, tau sigma of I is 5. When I do that with 2, well 2 goes to 1, I plug 1 into tau, and I'm going to get 2 again. All right. If I plug in 3, 3 goes to 2, 2 goes to 1. All right. If I plug in 4, 4 goes to 5, 5 goes to 3. And then if I plug in 5, 5 goes to 4, and 4 goes to 4. So the important thing to notice, 1, 2, 3, 4, 5. We get the numbers 1 through 5 again. Again, they're in some other order, but there are no repetitions and every number appears. We get another permutation. All right, so if we write that out as a matrix, so I have 1 through 5, then in total, 1 goes to 5, 2 goes to 2, 3 goes to 1, 4 goes to 3, 5 goes to 4, so 1 goes to 5, 2 to 2, 3 to 1, 4 to 3, 5 to 4. Okay. Now, this is kind of a long way to do that. So we want a faster way to compose permutations. All right, so to do this, if we're going to compute tau composed sigma, we put them into a column, and note, sigma goes on the top and tau goes on the bottom. All right, then to determine the composition, I start with I and I read down the column to find sigma of I in the second row, and then I move over, find sigma I in the first row of tau, and then I read down to get tau composed sigma of I. Right. It's much easier to see this with an example than it is to read instructions for it. Okay, so we're going to look at sigma and tau, and we're going to compute tau composed sigma. All right, so we put sigma first, then tau. It's important that when it is tau composed sigma, sigma goes first. All right, then to compose them, 1 goes to 3, 3 goes to 5, so in total 1 goes to 5. And then lather, rinse, and repeat. 2 goes to 1, 1 goes to 2, so 2 goes to 2. 3 goes to 2, 2 goes to 1, so 3 goes to 1. 4 goes to 5, 5 goes to 3, so 4 goes to 3. 5 goes to 4, 4 goes to 4 again, so 5 goes to 4 in total. Okay, so one of the things I've said about reordering permutations, you don't have to reorder the numbers. Okay, you could just keep them in their standard numerical order. If you do this as a function, this is what we call the identity permutation. Okay, it's denoted with the Greek letter iota, which looks a lot like an I without a dot on it. All right, but it doesn't do anything to any number. It sends it back to itself. So 1 goes to 1, 2 goes to 2, etc., n goes to n. Now, one of the reasons we like permutations is that they're invertible. I can undo a permutation. So, given a permutation sigma, the inverse is the mapping, we write it as sigma to the minus 1, so that when I compose them in either order, I get the identity. Okay, so what is an inverse permutation then? So given a permutation, its inverse undoes what the permutation does, like all inverses in this class. Okay, so that means if sigma maps I to j, then sigma inverse has to map j back to I. So looking at that, if I've got my sigma here, 1 goes to 3, well then sigma inverse has to undo that, so 3's got to go back to 1. If 2 goes to 1, then 1 goes back to 2, 3 to 2, 2 to 3, etc. All right, but we want to rewrite that in a matrix. So I'm going to take this information and I'm going to write it and I'm going to unscramble it, as it were. So I write 1, 2, 3, 4, 5. Okay, and then I tell where each element goes. So 1 goes to 2, 1 goes to 2, 2 goes to 3, 2 goes to 3, 3 goes to 1, 3 goes to 1, and then 4 goes to 5, 5 goes to 4, so 4 goes to 5, and 5 goes to 4. And that's not the easiest way to do this. There's got to be a faster way, and indeed there is. Okay, so to find the inverse of a permutation, if you think about it, when I look at a permutation, the first row gets mapped to the second row. This tells me where 1 goes, 2 goes, 3 goes, etc. Well, it's got to undo it. So the second row tells me where things should go in the first row in the inverse. So all you do to find a permutation, the inverse of a permutation, the first thing you do is you simply reverse the rows. Okay, so notice 1 goes to 3, so 3 goes to 1, 2 goes to 5, 5 goes to 2, 3 goes to 1, 1 goes to... This is the inverse permutation. It undoes what psi did. Okay, but we don't like our permutations written with the first row all mixed up. So once you've done that, you just unscramble it and you reorder the columns so that they're 1, 2, 3, 4, 5, and you move the parts accordingly. Okay, so why are we doing this? Okay, well, we're going to use this for encryption. Now, as a single step in an encryption, permutations don't give you a huge amount of security, as we will see. But when you start mixing them with other things, they give a great deal of security. All right, so we're going to be looking at different permutations and see how we can use those for encryption. Clearly, we're going to need the inverses in order to decrypt. That's why we need inverses. All right, we will look at a very elementary example, and then we will look at a more complex example. And if we have time, we will look at what's called super encryption, where you start mixing these types of ciphers with other ones. And so you have a series of operations that will give you first confusion, followed by diffusion, followed by confusion, followed by diffusion, over and over in these cycles. And then at the end of the day, you have a very secure cipher.